Okay, well, I want to tie up a couple of loose ends. And earlier, your book asked you to graph logarithms, your textbook, and I didn't cover that in my book. I don't normally do it in class because I figure that's enough is enough. We have too much to do as it is. So I left that out, graphing logarithms. But here I want to just touch base on it. If you look at an exponential function, let's look at e to the x. Okay, now I'm just going to rough sketch it here. And then, so this is, we'll say this is y equals e to the x power, where e is our natural base. All right, there's the graph of that exponential function. It's pretty typical. It has a horizontal asymptote along the x-axis. Now, if you were to look at the inverse function of e to the x is the natural log function. So the natural log function happens to look like this. And so this is y equals to natural log of x. It has a vertical asymptote on the y-axis. In other words, the graph approaches the y-axis asymptotically. It approaches but never quite touches over here. And you notice the logarithm function doesn't veer off in the negative range because the logarithms of negative numbers are not real numbers, so they don't graph on an xy plane. Now you would see something very similar. I think my book I wrote probably has 2 to the x and log base 2. And in fact, I guess I sketched those. Yeah, I didn't draw those electronically, but I did sketch those graphs using 2 to the x and log base 2. Very similar graphs. Now here's the neat thing about they're inverse functions. So a logarithm is an exponential function of its corresponding exponential function. And it turns out that inverse functions, the graphs of inverse functions have one neat commonality. All inverse functions reflect across this line here. So if I call this y equals to x, inverse functions are reflections across the diagonal line y equals x. So in other words, when you compare the two functions together, y equals x, this 45-degree angle line, is a line of symmetry between the two functions. That works for all inverse functions, as it turns out. And so it's just kind of a nice thing to know. So if for example, you wanted to get good at graphing exponential functions, then graphing logarithms would be a reflection across the diagonal y equals to x. All right, so that's kind of a nice little feature to point out. And we could take time and prove this feature here of inverse functions. I'm not sure it's worth it. The other thing I want to point out, in my book, I have a piece of graph paper. It's on page 283, as of the showing of this video. There it is. So I have this graph paper, which looks kind of strange when you look at it closely. It's semi-log graph paper. And so the x-axis is spaced equally, but the y-axis is spaced differently, unequally. And the spacing along the y-axis is a logarithmic scale. And so in scientific and engineering applications, that can be pretty handy. In fact, if Johannes Kepler had log paper back in the late 1500s, early 1600s, when he was trying to figure out how the planets moved in the sky, he was just before the telescope era. Kepler, one of the laws that Kepler discovered was that the square of the time it takes for a planet to orbit the sun is proportional to the cube of the distance. Now, I may have that backwards. I didn't look it up. It might be the cube of the time is proportional to the square of the distance. It's one of those two. Okay. You can look it up if you're interested in it. And you could actually discover that relationship by looking at how far the planets are from the sun and how long it takes for them to rotate around the sun. You could plot out the data of all the planets. If you plot it out on the right graph paper, you would see a line that would indicate that exponential relationship through logarithms. So semi-log graph paper, and is also called log graph paper, has some use in scientific and engineering applications. And if you want a sheet of it, go to my website. And on my website, I have that graph paper and other kinds of graph paper too. So semi-log graph paper can be bought. It's hard to find. It's probably pretty expensive. Or you can go to my website and just print a sheet off for free. So anyway, take a look at that. You do see logarithmic scales in other places. For example, if you have a guitar, you'll notice the frets near the nut at the top of the fingerboard are spaced out further apart, and as you get closer to the bridge, which is where your middle is where you're strumming it, the frets get closer and closer together. That literally is a logarithmic scale, and kind of like the semi-log graph paper, it's based upon logarithms, and in fact the tuning is based on logarithms. A piano, you could express all the frequencies of the notes on a piano through logarithms or exponential functions, and so that shows up there. Old-fashioned radios, FM and AM radios, where you twisted the dial and you saw the needle move back and forth. The numbers on that scale are logarithmic. And nowadays almost every radio is digital, where you see just a number pop up. But the old style, you see this needle move back and forth along a scale, and that scale was unequally spaced. It is a logarithmic scale due to the electronics and of the radios. So those things do appear out there. Okay, well, that wraps up this section, and now we go on to solving some equations.